Yeah, I ran out of time. Zoom school.
I wrote at the top of my paper, you have to determine whether axioms are consistent and independent. If you're a real mathematician and you're coming up with like a real system of axioms, and I think that was the main point from today's.
Yeah, I would say that was a very big picture takeaway. A somewhat still big picture, but getting more detailed takeaway is that when you create a model, you give explicit definitions for the undefined terms. Every axiomatic system has undefined terms, and that's all a model is. A model is just an explicit definition for the things which have been only implicitly defined via the axioms. And also that that if you're only barely paying attention, then you might have just thought like, what is he doing? Isn't he just doing coordinate geometry? But it like fundamentally isn't coordinate geometry, right? Because the verification that the axioms hold in the model cannot itself use any geometry theorems. Mm-hmm. Okay, so I hope those were the points that I had hoped to make clear. Maybe I should have just skipped the whole SAS as independent thing, but I did think it was cool. All right, that's all.
I thought that was good because it like explained what you were trying to do.
Wait, do you want to just do something right now? Anyone free for the next like 20 minutes? Because like we actually just didn't like get to the important part. I was gonna record a lecture, but we could just record it now with you guys here, and then I can just put it on Zoom. That would be more exciting. I mean,
that sounds fun.
I'll put it on Zoom. What the hell do you mean? I'll get the file. I'll extract the 20-minute segment that's relevant. I'll put it up on YouTube with all of your permissions, and then I'll assign it as a thing to watch. Instead of me pretending I'm going to eventually like do some OBS like crap. Let's just get this done with right now. Ready?
Wait,
first we have, or I guess Sam has a question.
How was Hilbert like satisfied with this? Was he just like, oh yeah, it's as consistent as numbers? Like, why does he believe in numbers?
Well, that's a separate problem. That's a problem for Tuesday, right? Today we're gonna reduce because we're reducing the consistency of Euclidean. What this entire thing is a reduction of the consistency of Euclidean geometry down to the consistency of arithmetic.
But like
certainly more confident about the
yeah.
So
I don't think you can absolutely prove the consistency of anything.
Hello, logic class. We're still here. You may have noticed. Woo woo. Sam just asked a question. Sam, ask it again.
Like you can't absolutely prove the consistency of anything. So like, why does Hilbert even care about this?
A little bit too strong, but yes, yes, it is important to clarify that what we have just done is itself a relative consistency proof. It is not a proof that the axioms, that Hilbert's geometry axioms are absolutely consistent. It is a proof that if arithmetic is consistent, then Euclidean geometry must be consistent, as interpreted, if we interpret Euclidean geometry as the geometry following Hilbert's axioms. And so, yeah, it's a reduction of the questions about consistency of Euclidean geometry down to the questions of consistency of arithmetic. But I mean, that's not nothing. I mean, here it is. Suddenly it's 1899. I mean, you might say, it's not an exaggeration to say that for the first time ever, we have proved that Euclidean geometry is consistent. Parentheses, as long as arithmetic is consistent. But you gotta start somewhere, and not only that, it's a clarification of precisely how much arithmetic one needs. You do not need all the real numbers. You do not need any transcendental numbers, for example, in order to verify the consistency. You don't even need all the algebraic numbers. You just need sort of some of them. Okay, wait. Let's go back to the presentation, because I think a lot of it is going to say this right now. So hopefully all this is being recorded. Yeah, so, okay, what we were doing in class, which we arguably got lost in the weeds a little bit, was a demonstration of how one of these, how one shows that a set of axioms is consistent. This is a very, very modern thing. It is really due to Hilbert that, that mathematicians start doing stuff like this. And really, you should see it as a continuation of the process started by Beltrami and Poincare and others to provide models for non-Euclidean geometry. Suddenly, people are providing models for all kinds of different geometries. All right, So wait, that was like the detailed part. Now we have like a 10-slide little just like wrap up, which is like probably the part that everyone in class really wanted, which is the part where we just like talk in big picture, grandiose words about, what's really going on. Well, I'll tell you what's going on. Metamathematics. That's what Hilbert says. All right, what is metamathematics? Well, first, let's decide what is math. Well, traditionally, math is just like, solving problems. Like if it's 3,000 years ago, math is just like, hey, I need to, farm this rectangle, whatever, what shape should it be, crap like that. But more rigorously in the era of Euclid, you could say that math is proving theorems. You will certainly find some perhaps arrogant math teachers or math professors saying that like the heart of mathematics is proving theorems. If you're not proving theorems, you're not even doing mathematics, maybe some might say. And to take it even one step further, coming up with axioms for your theory is also a part of mathematics. Okay, so mathematicians, these sort of three answers to this question, what is math, exist at three different levels. You're just solving math problems. You're proving theorems in general about the mathematical objects that you're studying. And even the very process of axiomatization itself is mathematics. So in this sense, Cauchy is doing mathematics and Weierstrass are doing mathematics when they are axiomatizing, calculus and coming up with epsilon delta proofs and things like that. So, okay, all of that is math. What does mathematics study? Mathematics studies mathematical objects. So numbers, angles, sets, functions, etc. Okay, Hilbert is taking this to a whole nother level now. He's saying that what we really need to be concerned with is metamathematics. Metamathematics is not just solving problems. It's not just proving theorems. It's not even axiomatizing your mathematics. It's actually proving facts about your axiomatization. It's not good enough to just provide an axiomatization. You need to prove that your axioms are consistent, and you need to prove that your axioms are independent. So metamathematics is like the study of the mathematical axioms themselves. That's the extent to which it's meta, right? Mathematics studies mathematical objects. Metamathematics studies mathematical axioms. And what Hilbert did is to really bring the attention of the world's mathematicians to metamathematics. He basically made metamathematics a part of mathematics. He declares, and he's very sort of forward-thinking in this respect and very influential, that this is now the responsibility of mathematicians to prove facts about their axioms. Okay, and so just to kind of, this is now just a very broad, this is a very broad sort of survey of this whole class up to this point. There are these kinds of questions like, what is the real mathematics? Is it analysis or is it geometry, etc. Well, from the time of Euclid to the time of Cauchy, and even probably beyond, everyone, the answer was clear to just basically everybody, that geometry was real mathematics, at least in the European tradition. Algebra and function stuff, they were all interpreted geometrically. Arithmetic and algebra were based on geometry. But what happens in the age of rigor is that analysis gets reinterpreted as arithmetic. And so we have now based calculus in arithmetic because arithmetic is a branch of mathematics that we have more confidence in than we do in geometry. And so one thing that Hilbert has done by constructing these very explicit models of the axioms of Euclidean geometry within arithmetic, he has kind of like now reduced geometry to arithmetic in some sense. If you believe in Hilbert's models, then in fact, like the truth of any theorem of Euclidean geometry is in fact a very, very, very complicated statement about the arithmetic of the points and the lines in his model. Okay, and so you can think of one thing that he's doing is just further reducing the sort of core objects of mathematics, right? You need not anymore believe in geometry, perhaps. You only need to believe in arithmetic in order to be sure that geometry is true. Okay, and all right, so this leads to sort of like these kind of final kind of closing slides. So ontology is a branch of philosophy which concerns like what exists. So when you're talking about ontology, you're talking about like what are the things of the world. And okay, so what is the ontology of mathematics? This is sort of I wrote this slide. this is my own kind of interpretation. Take any branch of mathematics, be it arithmetic, geometry, algebra, whatever. So here's what you have in that branch. You have the objects. In geometry, that's points, lines, and planes, and their properties, congruence, betweenness, etc. Then you have the axiomatization, because we must do things rigorously or we're doing nothing at all. So we have the objects, then we axiomatize. Then we have a bunch of theorems. The theorems are just what you can prove from the axioms. And then we have the models. So, you can ask these kinds of questions like, what are, you might, having seen Hilbert's models and having seen this sort of reduction of geometry down to algebra, you might start to think maybe just points really just are like ordered pairs of real numbers. Now, no one sort of thinks that, or most people don't think that. Most people sort of believe in like the reality of geometry, like that points and lines like really exist in some sense, but maybe you don't. You're now free to sort of relieve yourselves of the burden of worrying about whether points exist. Because as long as you believe that real numbers exist, then you're free to think of points as actually just being ordered pairs of real numbers. Okay, Hilbert's formalism has something to say about this. He is a sort of radical formalist. He says that if you want to know what geometry is about, I can't tell you. Anything that satisfies the axioms of geometry is equally well a point, a line, or plane. If you want to know what lines really are, you're a fool. That question can't be answered. All we can do is create axioms, and then if something satisfies those axioms, then it just is a line. So this is the other way in which Hilbert is influential for the philosophy of mathematics is this position. It's meaningless to ask what a point or a line really is. Everything that's important, anything that I can really say about points and lines has to be in the axioms. If it's not in the axioms, then it is irrelevant. And so the example that I always give is like color, right? You can just like set your GeoGebra defaults to be like all orange, and never change it. And so every freaking point and line and circle that you ever create is all orange. And some other person can do that with purple. And so one person might feel that all points and lines are purple. One other person might feel that all points and lines are orange. And they might have a disagreement about what lines really are. They might say, lines are orange. No, lines are purple. Well, no, because the truth of the theorems of geometry don't depend on the color. And that's why the color of the lines is not there in the axioms. And anything that's not in the axioms is just irrelevant. Any things which satisfy the axioms are just lines. Okay, 3 or 4 more slides, that's it. So what is, okay, so now let's just ask a kind of naive question. What is math? Isn't math about studying the true theorems? Isn't that what we go to high school for, to learn like some true facts about the world? No, sorry. Euclidean geometry and hyperbolic geometry cannot both be true. Therefore, this is kind of a repeat of some things that happened earlier in the presentation. We have to give up on truth. And so we can no longer, so the answer is, Hilbert's answer is that consistency is all we can hope for. Truth is too much to ask. And therefore, the only branches of math worth studying are the ones that are consistent. And until you've proven that your axioms are consistent, you're just wasting your time. And now this is often, this is a kind of a parody of that position. This is Bertrand Russell, who is not a formalist. He's a logicist. And he says kind of whimsically, as he kind of loses the battle, by the way, for hearts and minds, he says that pure mathematics consists entirely of assertions to the effect that if such and such a proposition is true, then such and such another proposition is also true. It is essential not to discuss whether the first proposition is really true, and not to mention what the anything is of which it is supposed to be true. So we don't ever talk about whether our axioms are true or not, and we also don't ever talk about what the things actually are that we're talking about. Thus, mathematics may be defined as the subject in which we never know what we are talking about, nor whether what we are saying is true. Okay, so this sounds insane, but this is actually what happens in the 20th century. All working mathematicians of the 20th century basically adopt formalism. And even if you talk to someone who's like truly like a mathematician kind of in more of a way than I am, like say Schwartz, for example, he's like an extreme formalist. If you've ever had any kind of philosophical conversations about math with him, they are hilariously, he is like a Hilbert straw man. If you ask him, well, like you give him some axioms, he's just like, I think I've said this already before, but it's like really true. Have I made fun of Schwartz yet this year in class? If you talk to Schwartz about axioms, he'll just be like, hey Schwartz, are these axioms true? He'll just look at you like, true? What does that mean? That's a bunch of nonsense. Axioms are true. Axioms just are. And he's just kind of like, give me the axioms, give me my paycheck, give me my peanut butter sandwich, leave me alone in my room. I'm going to prove my theorems. And then, that's formalism, right? Okay. But we still, in order to meet the sort of bare minimum, Hilbert says, we must show that our axioms are consistent. And so there's this kind of ladder of consistency, which can be thought of as, right, we show that hyperbolic geometry is consistent by building a model of hyperbolic geometry in Euclidean geometry. We've shown now via Hilbert that Euclidean geometry is consistent by constructing a model of it in arithmetic. How can we show that arithmetic is consistent? Well, we need to now build like a model of the piano axioms or something like that. We can do that within set theory. Oh, I hope set theory is consistent. That's really, really important because everything is resting on that now. Whoops. This presentation is supposed to come before the presentations on Frege and Russell. Oh man, it would really be a shame if someone found that there was like some problem down here. Okay. Yes.
Sorry. We've showed that Euclidean geometry is consistent if hyperbolic geometry is consistent also. But the rest of this ladder only works in one direction, right?
Yes.
Like,
yes.
We can't show that set theory is true using only arithmetic.
That's a
actually, can we be using neutral geometry here? Like, shouldn't Euclidean geometry be switched?
Wait. There's one more slide, and then I'm going to say goodbye to all the people who are watch this video. Then we can go off in other directions. Okay. Woo! So there is a quest. The quest is for consistency. And Hilbert sort of announces, note the year, 1899. He's announcing, or that's when it's published. It's probably from lectures delivered like, a year or two earlier. But this is pre-Russell's paradox. He's saying, we must show that our axioms are consistent. And so this now becomes, to Hilbert, the goal of everything. Demonstrate that our axioms are consistent, and to the extent that everything is resting on arithmetic and set theory, the most pressing problem in mathematics, as far as Hilbert is concerned, in 1900, is showing that arithmetic and set theory are consistent. And whoops, it turns out that set theory is inconsistent, as discovered and publicized by Bertrand Russell like 2 or 3 years later. So this can be seen, we can sort of see Hilbert as having like quite a lot of sort of foresight to be worrying about this. When almost no one else was worrying about the actual consistency of mathematics, Hilbert was. And to everyone's surprise, it turns out that mathematics literally is inconsistent. And so this is actually all kind of like a really big problem. Okay, hopefully that was only like about 15 minutes. People on the internet watching Logic, my own class, goodbye. I can make this a private link so not everyone will see it. So now you can turn it off, and now we can just